Today we are trying to understand C groups in Android. So what we are trying to understand here is, where does Android use C groups? What does Android use C groups for? So C groups, actually, what is C groups? C groups is a resource management program in the Linux kernel. What it tries to identify is allocate system resources or share system resources equally among the various entities. C groups is in fact the actual base on which the containerization of Linux or the container solutions that exist on Linux are being developed. C groups and namespaces, these are the two actual pillars of containers and virtualization in Linux. So especially now, let's go to C groups in Android. Android uses C groups mainly for two purposes. One, the low memory killer daemon. This is actually the daemon which monitors the system memory level, memory pressure level, identifies if the system memory is actually going low, and then based on that, it informs the low memory killer daemon to actually identify a process to kill it. It's different from the traditional that exists in Linux kernel, wherein the kernel itself actually identifies the process to kill and kills something. Here we are actually giving that giving that policy decision to the low memory killer, wherein the low memory killer identifies the process to be killed and kills it. So the low memory killer makes use of C groups to actually identify or measure or get notified of the pressure level, the memory pressure level. And the second place where Android actually uses C groups is for scheduling. Android categorizes its processes into various scheduling classes like foreground, background, etc., audio, etc., wherein based on which it actually tries to share the CPU, or it tries to give priority to the foreground applications or processes over the background processes. Android uses C groups to achieve this. So a traditional myth that existed is like Apple has this UI thread running with higher priority over other things, and Android doesn't have it. But if we follow the Android sources clearly, we see that the foreground tasks have a higher priority over the background processes. Anyways, let's move on to the next thing. Wherein in this slide we see basically the whole magic in Android, which corresponds to C groups, happens in the init.rc files, or the initialization scripts that get parsed during the Android boot up. The basic things, the whole setup is actually done there. The whole uh, configuration, etc., is already done there, and the source code just places the processes or the PIDs into the effective tasks, into the effective groups that they belong to. That's what the source code does. The effective groups are created in init.rc. The effective priorities, the time slots at which they run, or the time sharing priorities, everything is actually handled in init.rc. It's just that the PIDs of the tasks get written to the C groups through source code. That's it. So here, what we are seeing is how the memory C group gets mounted, and at what all points it gets mounted. The sysfs C group memory is one point where it gets mounted, and the memcg is one more point where it gets mounted. From my experience, from what I've seen, using the sysfs C group memory sometimes is something that it doesn't allow you to write to or read to, or work on those things sometimes. Especially, I've tried this with an Ubuntu system. So typically, the low memory killer uses the MMCG path for configuring its configurations, or for doing its configurations. So here, when it comes to memory, pretty much straightforward. Just you create this, and then the owner of this is root and system, and so no, nothing fancy, just uh, changing the ownership and the module permissions. That's it. So let's go to the source code of the low memory killer. So in this, if you see, what we need to see is, so this MCG SFS path is the MMCG. This is the path that, as I mentioned, that the low memory killer uses. And make note of this: the mem pressure watch level is actually medium, which Android uses. So basically, it tries to monitor the pressure level as medium, and once it hits, there is a C group event that it receives using an event FD, and then it goes through. Let's see how it happens. So the major function uh, that that starts this configuration is init-mp, wherein you have the sysfs group path, or the C group path where it is mounted. uh, the memory pressure level is open. You have another C group event control, which is actually where you write into the file descriptor of the event FD and the pressure level, based on which the event is triggered. You can see that here we are actually writing the event FD file descriptor, the file descriptor corresponding to the memory pressure level, and the level string which corresponds to medium. This is actually what is written to the event control FD. Okay, and what also is being done is the file descriptor of the event FD is actually added here. And with this, what happens is, whenever there is a change, or whenever the event FD in the kernel gets triggered, you get to know that there is a low pressure event, and then the memory pressure event handling gets kicked in. So the MP event is the function which actually does that, and you can see that. So this gets called when you have the pressure level going less. Okay, and what MP event does is actually goes through find and kill process. That is what it does. Simply, it just finds out a process which it can kill. So here you can see that low memory killer uses C groups to identify the pressure level and get notified by the kernel when the pressure falls below a certain level. Now let's go to the scheduler policy. Major part of scheduler policy is actually something that's handled in the init.rc, which, as I mentioned earlier. So if you see the init.rc carefully, you can see here that Android basically uses the CPU C groups to achieve the scheduling benefits, or to categorize the scheduling things. And what it does is, the basic CPU control for the root node of it is 1024, and you have the real-time runtime as 800K, and the CPU real-time period is 1000K. What this means is, when you have a time period of 1 second, the real-time tasks in this CPU group or in this C group get a time share of zero point 0.8 seconds, which means that 80% of the CPU is being assigned for real-time tasks in the C group. Okay, now we have another it's like another level of C groups in the same root, which is called as BG non-interactive. These are background and non-interactive tasks, and the CPU shares for this is written. The CPU shares for this is configured as 52. What this means is, this C group basically gets a CPU share of 20. It's like 5%. It's like 52 by 1024, where 1024 is the base of it. So it's like nearly 5% of the CPU is assigned to the C group when you have some tasks in the C group. And even in this group, when you have 5% of the CPU being assigned to the background and non-interactive tasks, the real-time tasks which are there in the background C group still get 70% of the CPU time if there are any real-time tasks in this CPU C group as well. So that means that real-time tasks which are there in both the foreground or the background non-interactive C groups still get a fair share of CPU. But as I said, right, the background CPU share is just 5%, whereas the remaining percent is actually for the other CPUs, the foreground ones. So this is the whole magic is here. The whole magic happens in init.rc for the scheduling class. Let's now go and see the shed policy source code wherein we see how this happens. Add tid to group is the function which actually handles this. Yes, add tid to C group. This is where you add a tid to a C group. So this is the function. So what this does is it writes it writes a particular given tid to the corresponding C group. That's it. So as I said, right, once we have the infrastructure ready in init.rc, all that the source code does is actually write the PID to the correct C group. So this function, you can see that it gets a TID and the file descriptor which corresponds to the C group which it needs to be put into. Okay, now let's see if I have to do a set shed policy. This is what Android uses to actually set a scheduling policy on a particular process. And then what it does is it checks whether the scheduling policy is background, foreground, audio, and all that stuff. And based on that, if it is background, you have a file descriptor which corresponds to a C group which is open for background files for background tasks. And then for foreground audio and audio sys, you have a foreground file C group which is all for which we have the file descriptor open. And then all that we do is we just pass that file descriptor and call add tid to C group. And what this does is it takes the thread ID and puts that particular thread ID into the corresponding C group. Now let's see how do we get the FG C group FD. So you can see here the FGC group FD is something like you open the dev CPU control tasks from where you actually get this, and the background non-interactive task is where you get the BGC group FD. So once you have your setup done in init.rc wherein you have created the necessary C groups for tasks for foreground and background, and you have set the period at which they need to run and the CPU shares. That's it. All that you need to do is simply set the put the thread ID or the process ID into the particular C group, and everything is taken care of by Android. So that's how it goes through. So as I mentioned, Android groups process into the following groups based on the scheduling policy. It's like background, foreground, system, audio app, and audio sys. So when you see the source code, you can see that background and foreground are the actual C groups that we make use of, but the remaining things are the classes that are just there. Probably we will have Android make, do some changes for it in the future. That's it. And these are some of the references: shed policy, process.cpp. These are some of the source code references and reference of an article which corresponds to Android scheduling. That's it for today. Thank you.